In this section, I want to get into a little bit more about the strength of a linear correlation. So this is section 4.2. Make sure you have your notes in front of you, you're following along very closely, and your cell phones are turned off and put away. So we're going to introduce a numerical value that we use to indicate how strong those two numerical variables are associated when you have a linear relationship. And the name for that is called the correlation coefficient. So this is a really important term that we're going to use throughout the rest of this unit. And the definition, we say it's a number that measures the strength of a linear relationship. If it's not a linear relationship, then we wouldn't use the correlation coefficient. So the first thing we have to do is identify that it's linear. The notation for it is a lowercase r. Now you will notice when we use StatCrunch that they use a capital R. Some textbooks do that, but I think the standard way is a lowercase r, so that's generally when I'm writing these what I will use. R always takes values between -1 and +1. So as an inequality, you could say R has to be between -1 and +1. If it's +1, that means you've got a perfect positive correlation. If it's -1, you've got a perfect negative correlation. So a value close to -1 or 1 indicates that you have a strong association. The closer you are to 1, the better your association, whereas an R value closer to 0 indicates a weak linear association. In these pictures below, you can see the different sort of scenarios that you might have. So the perfect positive correlation, so if everything was perfectly lined up. Now in the real world, that doesn't happen, but R equals 1. And you can kind of think of it as the slope of the line. That's not exactly what it is, but it's related to that. So in thought, you can kind of think of it the same way. Whereas down here, this would be a perfect negative correlation. This would be an R value of -1. A strong positive correlation, now what do we define as strong? That's a little bit subjective, but I would say R is close to 1, maybe it's like 0.89 or something, 0.75. A weak correlation, positive though, would be R is close to 0, but R is still positive in this example. So it's a positive correlation because the trend still tends to be up, but there's a lot of space between the graphs. So it's a weak correlation, but because it's positive, the R value is going to be positive. It's something like 0.35 or 0.2 or something like that. No correlation, that would be R equals 0. A weak negative correlation, R again is close to 0. However, because it's negative, the trend is downward, then we would say in that case R would be negative. So R would be like negative, I don't know, 0.3 or 0.2 or something, but it'd be negative and close to 0. Strong negative, you would have R close to -1. So that's the negative analogous to the one we had up here. All right, let's do an example. In this set of graphs here, it says consider the following scatter plots with the correlation coefficient for each plot given. Now, by the way, they have to give you the correlation coefficient, or we're going to use StatCrunch to obtain it. It's a little bit of a complicated calculation, so we're not going to worry about calculating it by hand, but we will use graphs to do some matching and things like that. So hopefully you see in this picture we've got a positive correlation, but it's fairly weak. The graph, or rather the points are pretty spread out. So the R value here is 0.10. It's positive, but it's fairly close to 0. We have a slightly stronger correlation here, still positive, but not particularly strong, but it did go up. It went to 0.33. Of the three pictures, this is certainly the strongest relationship, and it's definitely positive, and the R there is 0.89. So you can see how as the points got closer and there was less of that vertical scatter, the R value got closer to 1 in this case because these were all positive correlations. So it says note that as R, let's say as R gets closer to 1, there is less vertical variation in the data. So we have a stronger trend as we went this way with the pictures. couple of notes about the correlation coefficient. Changing the order of the variables does not change R. R you can kind of think of like a distance. That's sort of what it is. And it's a little bit like standard deviation. We thought about that earlier with a single variable. So it's kind of how do those variables relate to each other? How strong is that correlation? So swapping the x and the y does not change those distances, in other words. Adding a constant or multiplying by a positive constant also does not affect the R value. R is unitless, which is one of the few things where we talk about in this class where there's not units for it. And R is only useful to measure a linear trend. Like I said, if you don't have a linear trend, the R does not apply. It would be some other way to measure the strength, and that's beyond the scope of this class. So all we're going to worry about is linear data. If the data for some reason is not linear, then none of this applies. All right, I think that's all I wanted to talk about for R. So tomorrow we'll look at this in class a little bit and talk about how to get that R value from StatCrunch and do some interpretations with it. So I'll see you then.